Hello everyone, welcome to the new video where we will discuss a deep learning paradigm called model compression. In our journey, we will cover aspects like what model compression is, the various model compression techniques, and the applications of these techniques. So, what is model compression? Before going on that part, let us first discuss some history. With the advent of high-performance computing and the development of GPUs, deep models have continued to dominate the field of computer vision and natural language processing, as we can see from this image showing the results of the ImageNet challenge, which involved training a model that can correctly classify an input image into thousands separate object categories. It can be seen that the model error continued to decrease through the years, but it also introduced a new problem. As evident from the figure, the model size was merely increased to capture the minute nuances of the images. The model's accuracy increased, but at the cost of the size and computational complexity of the model. Therefore, we needed to reduce the size of these models and make them smaller to run on resource-constrained devices like smartphones or edge devices. Following the trends, when transformer networks were introduced for natural language processing tasks, they required huge storage space and computation power, which are often unavailable. If we try to use smaller models, the accuracy will decrease, and there has to be a trade-off between accuracy and model size. So, is there any way to make models smaller without reducing their accuracy? This is where model compression comes to help. So, what is model compression? Model compression is the process of reducing the size of a machine learning model without sacrificing its performance. It is a crucial technique for deploying machine learning models in various applications. So, what are the aspects for which model compression can help us? Model compression can help reduce the model storage requirements, which can enable quick deployment of these models, especially for cloud-based deployments. Another aspect of model compression is to improve the inference speed of the model, since smaller models require less computing power and can generate results faster than larger models, which is essential for real-time based applications. The other aspect of model compression is to improve the model portability, as smaller models are more accessible to share and deploy across different devices and platforms. In this section, we will cover various widely used model compression techniques. Here are the four most popular model compression techniques. First is pruning, where we remove redundant connections that do not contribute significantly to the model's performance. The following technique is quantization, where we reduce the number of bits required to represent each bit. The following technique is low rank factorization, where we decompose a large weight matrix into smaller matrices, reducing the computations. Last, we have knowledge distillation, which transfers knowledge from a more extensive network to a smaller one. Let us explore these techniques in detail. The first technique is pruning. In pruning, we remove redundant and non-informative weights or connections from a deep neural network. Pruning can be implemented in two ways: weight pruning and neuron pruning. In weight pruning, we remove the weights with small magnitudes or connections that contributes less to the overall network performance. In neuron pruning, we prune the neurons or channels that do not contribute significantly to the model's performance to reduce the model size and computation cost. Let us visualize these methods of pruning. As we can see, this is a fully connected neural network where each neuron in the current layer is connected to the neurons of the following layers. In weight pruning, we remove some weights based on specific criteria, like the value of the weights. Next, we see the neuron pruning method. Let us take the same network, but this time we prune the neurons as shown here. We remove the neurons from the layers if they do not contribute much or provide redundant results. Now, let us see how pruning is implemented. In pruning, we aim to identify unimportant parameters, which can be done by ranking the model's parameters by their magnitude and removing the most minor parameters. Once the insignificant parameters have been identified, they can be removed from the model using a variety of different methods. One common approach is to set the weights of the unimportant parameters to 0. Another approach is to remove the insignificant parameters from the model altogether. Pruning can be applied during or after training. During training, pruning can be incorporated as a regularization technique, and after training, pruning can be used on an already trained model to compress it further. Note that fine-tuning of the model is required after pruning to restore the model's performance. Now, let us see some pros and cons of pruning. Pruning reduces the model size, which is crucial for deploying models on resource-constrained devices. It also reduces the model's computational complexity, leading to faster inference times. It can also improve the generalization of the model due to the regularization and reduces overfitting. But there are also some challenges while implementing pruning. It is pretty challenging to come up with the decision of which weights, connections, neurons, or channels to prune without reducing its performance, which other way might lead to underfitting. The pruning criteria must be chosen carefully to balance between model size reduction and performance preservation. Next technique is quantization. Quantization is a model compression technique that involves reducing the precision of a machine learning model's parameters. This can be done in a number of different ways, but the most common approach is to convert the model's parameters from floating point numbers to integer numbers. Quantization can be applied to a variety of different machine learning models, including neural networks, decision trees, and support vector machines. It is a powerful technique that can be used to reduce the size and complexity of machine learning models without sacrificing too much performance. Let's take a simple example. Consider a model with a single weight matrix that is 100 by 100 elements in size. Each element of the matrix is a 32-bit floating point number. This means that the total size of the matrix is 100 by 100 times 4 bytes, which is equivalent to 40,000 bytes. If we quantize the weights of the matrix to 8-bit integers, the size of each element is reduced from 4 bytes to 1 byte. This means that the total size of the matrix is reduced to 100 times 100 times 1 byte, which is 10,000 bytes, which is a 4 times reduction in the model size. Let us talk about the various approaches to quantization. One approach is uniform quantization. This is the simplest quantization technique, and it involves dividing the range of values that the model's parameters can take into a number of equal intervals. Each parameter is then assigned to one of the intervals, and a single integer value represents the interval. The other approach is non-uniform quantization, which is more sophisticated than uniform quantization and takes into account the distribution of the model's parameters. This allows the quantization intervals to be sized more efficiently, which can lead to better performance. Quantization can be performed during training or after training. During training, quantization can be incorporated as a regularization technique by adding a quantization loss term. The model is trained with quantized weights, which help to ensure that the model does not lose accuracy after quantization. After training, quantization can be applied to an already trained model by mapping the floating point values to the desired lower precision representation. Now, let us see some pros and cons of quantization. Quantization reduces the memory requirements of the model, allowing for more efficient storage and deployment on resource-constrained devices. It also reduces the computational complexity, leading to faster inference time. Quantization also faces some challenges. There can be a potential loss of model accuracy due to reduced precision of the parameters. It can also introduce quantization errors that may affect the performance of the network. The following technique is low-rank factorization. Low-rank factorization is a technique that involves decomposing a large weight matrix into a product of smaller matrices. This can be done using a variety of different methods such as singular value decomposition and non-negative matrix factorization. Once the weight matrix has been decomposed, the smaller matrices can be used to approximate the original weight matrix. The approximation error can be controlled by the rank of the smaller matrices. A lower rank will result in a smaller model, but it will also result in a larger approximation error. Let there be a weight matrix A with dimensions m by n. that can be factorized into two smaller matrices U and V, where U has dimensions n by R and V has dimensions R by n, and R is the desired rank. Choosing a lower rank R reduces the number of parameters from m into n to m into R plus R into n, resulting in a smaller model size. Now, let us see some pros and cons of low rank factorization. Low rank factorization reduces the memory requirements of the model by approximating weight matrices with low rank matrices and can provide faster inference times. It reduces the number of parameters, and the structured nature of low rank matrices allows for more efficient computations. But it also faces some challenges. The decomposition process can be computationally expensive, especially for large-scale models, and finding optimal low-rank optimization is challenging. The performance of the compressed model may vary depending on the chosen rank. Overall, low-rank factorization is a powerful and versatile model compression technique that can be used to improve the efficiency and performance of machine learning models. The next technique is knowledge distillation. Knowledge distillation is a model compression technique that involves transferring knowledge from a large and complex model called teacher model to a smaller and simpler model called student model. This is done by training the student model to mimic the predictions of the teacher model. Here is a figure demonstrating the knowledge distillation. As we can see, we have a larger teacher model and a student model, and the knowledge can be distilled from the fully connected layers of the teacher model to student model. So the student model is typically trained on a dataset of the teacher model's output, and it learns to reproduce those outputs without having to access the teacher model's parameters. This can significantly reduce the size of the student model without sacrificing too much performance. There are a number of different KD techniques that can be used, including the first is offline distillation, which is the most common type of knowledge distillation, which involves training a student model to mimic the predictions of a pre-trained teacher model. The second is online distillation, where the teacher and student models are trained simultaneously. And the last one is self-distillation, where the teacher and student models are the same. Another approach is to transfer the teacher model's intermediate representations or feature maps to the student model, which can be done by adding additional loss terms that measure the similarity between the feature maps of teacher and student model. By mimicking the intermediate representations, the student model can benefit from the teacher's learned representations and capture more nuanced patterns in the data. Knowledge distillation can be combined with other compression techniques to achieve even higher compression levels. Another technique is Huffman coding. Huffman coding is a lossless data compression algorithm that assigns variable length codes to the different symbols in the model, with more frequently occurring symbols being assigned shorter codes. This can significantly reduce the size of the model without sacrificing any information. It is a particularly effective technique for compressing models containing many redundant data, such as in case of natural language processing models and image recognition models. Let us take an example. Consider we have A, B, C, D, and E as symbols in decreasing order of frequency. To construct the Huffman tree, we will first take the least frequent characters, which in this case are D and E. We join them and select the next pair B and C. Their combinations are combined with A to complete the Huffman tree. After generating the tree, we assign weights to the edges. So the left edges are given 0 while the right edges are provided 1. We can develop the Huffman code for that leaf node by traversing the tree and concatenating the edge assignments. In this case, the Huffman code for A will be a 0, and for others we can use, for example, for B we can use 1 0 0. In this case, we can see that the most frequent element A has a shorter Huffman code than the other Huffman code. So, concluding the model compression techniques are complementary to each other. It can be applied to pre-trained models as a post-processing step to reduce the model size and increase inference speed. It can be applied during training time as well and the resulting models are both memory and energy efficient. Let us discuss the three-stage compression pipeline, or which is also known as the deep compression pipeline. The first stage of decompression is pruning, which reduces the number of connections in the network by 9 times to 13 times. The second stage is trained quantization. The weights of the network are quantized to enforce weight sharing. For example, weights may be quantized from 32 bits to 5 bits. And the final stage of decompression is Huffman coding. It assigns shorter code words to more frequently occurring weights and longer code words to less frequently occurring weights. By combining these three stages, deep compression offers a powerful approach to reducing the storage requirements of neural networks. Now, let's see some applications of model compression. Here are the model compression statistics. We have results for 4 models with their top 1 and top 5 errors and parameter sizes. As we can see, we have used 4 models which are LeanNets, AlexNet and VGG16. So the first row represents the vanilla models without any compression, and the second row represents the compressed model statistic. As we can see that there is not a significant change in the errors. In fact, in some cases the error has reduced due to the fine tuning, but there has been a significant improvement in the model sizes. As we can see, the highest rate was observed in VGC16, which is a fairly larger and complex model, which achieved a compression rate of 49 times, and AlexNet achieved a compression rate of 35 times, and then the LeanNets achieved a compression rate of 39 to 40 times. Now, talking about the applications of model compression, we find its extensive use in image classification. For example, low-rank factorization has been used to compress deep neural networks for efficient image recognition. Nowadays, the most popular technique used for model compression is knowledge distillation, where the knowledge is distilled from a bigger teacher model to a smaller teacher model, to student model. For example, the knowledge from ResNet 50, which is a fairly large and complex model, the knowledge from that can be distilled to a smaller model, for example, MobileNet V2, which is a much more complex model than ResNet 50. Another domain where model compression is being used is natural language processing. Model compression is an active area of research in NLP, and new techniques are being developed all the time. Currently, knowledge distillation is used to compress large language models, enabling faster inference and reduced memory requirements. One of the most important aspects of model compression is its use in resource-constrained environments like edge devices. Model compression can help in reducing latency, improving energy efficiency, and reducing memory footprint and bandwidth requirements. As model compression techniques continue to improve, we can expect edge devices to be used in a broader range of applications such as self-driving cars, smart cities, and industrial automation. Moreover, model compression techniques can also be combined with transfer learning to leverage pre-trained models and adapt them to new tasks or domains, which is also known as the lifelong learning. In the future, more efficient and effective transfer learning techniques can be developed that incorporate model compression. Here are some examples of how model compression is being used in the real world. Google Translate uses model compression to reduce the size of its translation models so that they can be deployed on mobile devices and other devices with limited computing resources. Facebook AI uses model compression to reduce the size of its image classification models so that they can be deployed on mobile devices and other devices with limited computing resources. Similarly, Amazon Web Services, or AWS, offers several model compression services that can be used to reduce the size of machine learning models before deploying them to the cloud. So, in conclusion, model compression is a powerful technique that can be used to deploy machine learning models in various applications. By reducing the size of machine learning models, model compression can help to reduce storage costs, improve inference speed, and improve model portability. Thank you for your time.